Thanks, Ian. So it's great to be here. This is going to be kind of a scary talk, but I promise it has a happy ending. So Sam gave us a really nice introduction. Sam gave us a really nice introduction to what we in the instrument building community are doing on the hardware side of things to break this 1 meter per second barrier. I'm going to give sort of the second half of that story, which is what we do once we've built the hardware. How do we use that instrument? We've been talking also a lot about breaking this 1 meter per second barrier. And let's take a second to think about what that actually means and why there is this barrier. So the only reason this barrier exists right now is that empirically we found that the hosts of existing spectrographs all sort of bottom out at the 1 meter per second level. And for some stars, we think the star is not the limitation, it's the instrument. And for those stars, especially the quiet stars, we want to make sure that our instruments are better than the best stars. So the idea is that we've heard a bit about what RV precision means and what RV error means. And in this context, we always want to be trying to be photon noise limited. So that's the fundamental limit. You can do nothing about the number of photons you can collect, but you want to bring down everything else so that you're only limited by this fundamental physics. So once again, to revisit what we're doing here, there is a star really far away that is wobbling just a very little bit because there is a small planet around it. And we collect the spectrum of the star in high resolution, watch it move back and forth, get red shifted and blue shifted, look at the period of that shift, look at the movement of the lines at, as we said, 1,000 to a 10,000th of a pixel, and then infer the properties of the planet that's going around it. Sam showed us that this is a very, very difficult measurement. It's basically measuring movements across a few atoms in your silicon lattice, which should blow your mind. But for a bit more of a real world example, what this corresponds to is about the speed of a desert tortoise. So that's slow, that's slower than you walk. And that's how fast the star is moving light years away. So very, very challenging measurement, and we should not underestimate any of the error sources that could creep in. So this is why we have this error budget-based approach where we try and think of every source of error and how to handle it. So the basic philosophy of these next generation instruments, and I'm going to talk mainly about the stabilized instruments, not the iodine instruments, for two reasons. One, that's what I work on. Two, all of the new next generation instruments are stabilized, fiber-fed, thermally stabilized vacuum chamber instruments. So the idea there is that because there are so many sources of error, you want to kill them at the source. And so you stabilize everything that you can in hardware. So Sam talked about putting it in a vacuum chamber, having millikelvin thermal control, really thinking about the illumination of the spectrograph. There's a host of other things. But your job is not done once you're done building that instrument. So what you've done is stabilized everything to some level. That level is not zero. All of those things still exist at some level. So you want to make sure you beat down everything to some acceptable level, but for everything else that you couldn't correct in the hardware, like the star, for example, or the motion of the Earth, you want to build in diagnostics so that you can track these variables and then correct for them in your analysis. So the software really is the latter half of this story. Pipelines are often sort of underestimated, as you know, we'll do that once we get data. You cannot do this for this kind of spectrograph. The pipeline is as much part of the instrument as all of the optics. So Sam showed us our scrambler that is now on a few different instruments. And I want to emphasize that while this shift is very obvious, and this looks rock steady, this is the scary part. Nothing is rock steady at this level, right? At a 10,000th of a pixel, this PSF is also moving. You just can't see it. And so when you measure the radial velocities, you will measure a little bit of that shift. The question is it acceptable? Is it below your 10 centimeter per second level planet that you're trying to measure, or do you need to correct this out? And think about it really hard when you're writing your software. So I work a lot on writing data pipelines for these next generation instruments. And so to do extreme precision radial velocity, you need an extreme precision pipeline. This is a little schematic showing, not a little, it's kind of a big schematic, showing the pipeline for the Keck Planet Finder instrument in particular, which is actually borrowed from the NUID idea. But all of these instruments will need to do all of these things. And you don't need to try to read it, but I guess the point of this slide is this is complex. Many of these squares are pretty unknown. We don't really know how to deal with them. There's also this little dotted line that I drew, which is the stellar activity correction, which we really are not experts at yet. We're getting better at it. The more high resolution data we get of these stars over different time scales, the better we understand it. And we can try to correct for it. But this is something we're definitely still learning how to do. So just to motivate the rest of the analysis that we're going to talk about, let's really understand how we measure radial velocities. And Sharon already showed this cartoon. So the idea is that you have your stellar spectrum, and you want to measure each line has some information content, right? Each line has moved with the star, was formed in the atmosphere of the star as it was moving in response to the planet, and has some shift. So you want to measure the shifts of all the lines. Individual lines are kind of difficult to measure because they're sort of noisy. And so what we do is instead make a very specific custom mask. So you think about the best lines that you want to use for your radial velocity analysis, and you shift the mask basically across the spectrum in very tiny steps, so sub-pixel steps. And at each step, you multiply it with the spectrum, building up this cross-correlation function. So at the end, this cross-correlation function is basically an average stellar line, depending on what mask lines you've picked out here. Then you fit it with a Gaussian, and you measure the peak of that Gaussian, and that is your measured radial velocity for that epoch. The nice thing about the mask technique is that you never have to touch the spectrum. So imagine if instead you move the spectrum back and forth. That's really difficult because your spectrum is only sampled at certain points. And anytime you interpolate it as you shift it, you're changing the shapes of the spectral lines. And as we established, we really care about the shapes and positions of these lines. So you don't want to introduce error just by moving them around. So you leave those alone. And because this is a numerical mask, you can reconstruct it at a sub-pixel level really well. So this works very well for sun-like stars, where you have a nice continuum, you have nice clean lines. It sort of breaks down for M dwarfs, where it's A, we don't really know all of the lines that go into an M dwarf atmosphere, and B, there's not a nice continuum to separate the lines. There's all these horrible blends and forests of molecular species. And so often for an M dwarf, what you do is instead of making a mask, you add up a bunch of spectra and create a really high signal to noise template that then you can move around. You still incur some errors from interpolating that template, but because it's so high signal to noise, you sort of beat that down. So this is what we're going to try to do. And we spent all of this hardware effort making the lines really stable. And so now we're going to benefit from that, which means that we can trust that these lines, if they're varying, are varying from an astrophysical origin, not the temperature changing in the room that your spectrograph is in. So let's get to know our data and love our data. It has lots of imperfections, but this is the best we can do right now. So this is what that data looks like. So this is a commissioning frame from the Habitable Zone Planet Finder spectrograph that Sam and I both work on. And Sam showed some examples of this. This is real data. So what you get is this cross-dispersed Echelle spectrogram. So the Echelle spreads out the light in the dispersion direction, and then you have either a prism or something similar to separate out the orders in this direction. And you sort of read it like a book, left to right and top to bottom. That's how the wavelengths go. So already in this first raw image that you take, all of this hard work that you did to build a very stable, very optically pristine spectrograph, you can see all of the benefits of that. So here's a little zoomed in region, and what you can see here are the 3 fibers that we have in HPF. So this is the sky fiber, not a lot of light in it, which is good, but you can see some of the sky emission lines. Here is the stellar light. You can see the continuum there, and there's your laser frequency comb making a very nice forest of lines to calibrate again. So what you can see right off here, like Sam said, each line is actually an image of your input aperture, whether that's a slit or a fiber. We actually have a slit on top of fiber, but looks like a slit. So each line is actually an image, which is also true of the stellar lines. There's low aberrations. This is actually a very nice clean image. Because it's hard to tell if it's really clean, here is an example of not a clean image. And you can see there's horrible ghosts, these streaks, lots of scattered light. Any light that you add on top of your stellar lines obviously detracts from your ability to measure those very well. So this is an example of what you shouldn't have. So we have these 2D frames. Now we have to do radial velocity analysis, but sort of starting at the first step is image processing. And a lot of you might have done basic image processing on frames that you took. This has similar steps to basic image processing, but has some extra things that we have to be careful about at this level of precision. So you start with your CCD image. That's what we're calling a level 0 science image. You also, at the same time, have gathered all of the information about that observation as you were taking it. So things like the weather conditions, the temperatures all around your instrument, air mass, all of that stuff. So you take the raw image, which looks like this, is a 2D image. You take out the bias for a CCD, and then you normalize it using the flat field. And so these are pretty regular steps, but you have to be careful about a few different things. Things like bad pixels, this is where you account for them. Keep in mind bad pixels change over time, CCDs degrade. You also have to worry about the edges of these flat fields. That's sort of a nuance, but very important for fiber-side spectrographs. And the other thing is pixel to pixel variation. So you don't want the fact that the CCD pixels are not exactly the same to change how you measure the star. And so I'm going to do a little aside on how imperfect CCDs are. This is really scary because we've actually gotten really good at making CCDs. CCDs are great compared to, say, near-infrared detectors like H2RGs, but they're still not perfect. So one of the things I worry about a lot is the fact that while pixels are supposed to be perfectly shaped and all have the same size, that's actually not true. So this is an exaggerated cartoon, but the real pixels are actually just a little bit bigger or a little bit smaller than they're supposed to be. What that means is if you put in, say, this black stellar spectrum onto your detector, what you actually get is the red line. So you think you have a certain amount of flux, but you're collecting just a little bit or a little bit less. And so what that does is adds white noise to your spectrum that you measure. And also your wavelength calibration is now wrong, because just a little bit wrong, but wrong enough that you care, because you assumed a perfectly rectangular grid when you made that wavelength calibration. So these are some of the nuances of what we worry about. Another problem is charge transfer inefficiency. So if you remember from an optics class you took or something, that CCDs transfer charge in this bucket method, so from one to another, and the idea is that the charge just gets shuffled and then read out at the end. The problem is that the CCD is not perfect at transferring this charge. So every time it transfers it, it loses a little bit of light. And so you start out with a certain profile, but then you sort of smear it out as you go. This is bad because your lines are now skewed in the direction that you read them out. And again, we care about the shape of the lines. And it can mess with the level of the continuum that you're trying to measure. The plan is to try to correct for this, but what really makes it complicated is it's flux dependent. So depending on the amount of energy that's in a pixel, how much gets left behind is determined. So this is a complex problem as well. Not something you can easily model out. Another problem with CCDs is that they have fringing in the redder wavelength. So we're getting really interested in M dwarfs, and a lot of the sort of optical CCDs, optical instruments are going red to 800, 900 nanometers. The problem is that these CCDs have a certain thickness, and if you have a very red photon, it tends to bounce around inside your CCD, and instead of landing at the spot it was supposed to, it bounces a few times and lands at a different pixel, which gives you sort of this red structure. So that's a flat. It should be flat. But it has all of this extra structure on it. You can correct it out, but this can be expensive because unfortunately the fringing also varies over time. At this level, everything varies. So things we worry about, this is actually best corrected in hardware. So you buy a better CCD, and people are beginning to be able to make CCDs that minimize this to an acceptable level. All right, so we have our image. We've subtracted the bias, corrected the flat field. Now we want to reduce the data. So from a 2D image, we want 1D spectrum. So the way we do this, first of all, is to trace the Echelle orders. And depending on your cross disperser, they can be really curved. So this is porous with a prism cross disperser that makes the orders really curved. This is 4,000 into a few thousand pixels here. And so one thing you worry about a lot is that your orders aren't perfectly placed on your pixels. So they don't always occupy a rectangular line on your pixels. And so one way we do this is to rectify this order onto a rectilinear grid. This is very hard because you want to be sure, again, you're not messing with the shapes of the spectral lines or the flux levels. You also worry about slit tilt. So you might rectify it, but your real slit images might still be a little bit skewed. So you can try and correct for that. There's also crosstalk between orders. This is really bad because you have a laser frequency comb and your star, and a little bit of light from one fiber leaks into the other fiber. So underlying your star spectrum is a really faint laser frequency comb spectrum. So you want to try and correct for that as well. You want to minimize scattered light and ghosts, but you also want to do things like take out cosmic rays. That's sort of a thing you do even in non-precision astronomy. And so the way we do this is to do an optimal extraction, which basically means you look at the profile of the order in this space, map it out, and then extract a nice clean spectrum without bad pixels or cosmic rays. Then we get to the wavelength calibration. Okay, so we have our flux array, 1D flux array. Now we want to know what each pixel corresponds to in wavelength. Sam already introduced the different things we use. This is a picture of the Harp-Snort laser frequency comb in the early days. So basically what you get is this really nice grid of lines. The red dots are the actual data points. And so I'm not really going to talk about lamps very much, although we still use them a lot. I'm going to talk about this future calibration source. So the idea is that you fit each of these lines with a Gaussian, and you know where the line is supposed to be. You know the absolute wavelength of the line. And so then you measure how much it has moved from the absolute wavelength. A weird problem with laser frequency combs is that they're actually kind of too good because the lines are so narrow. They're just about sampled well enough. So you can see for this line, for example, you didn't even catch this peak. For most of them, you're not catching the peaks, and you don't really, if you drew this would be a weird shaped polygon. And so that's the responsibility of the data analysis pipeline, to take all of this line shapes and make sure that it figures out the centers of each of these lines really, really well to maintain that, you know, less than 1 centimeter per second comb precision that is intrinsic. You want to get as close to that as possible. Okay, so now we have extracted spectra that are wavelength calibrated. And they have a lot of systematics in it still. So if you just measure the radial velocity of the spectrum as it is right then, as Sharon said, what you're probably going to measure is the barycentric velocity of the Earth. So you want to do several steps of correction. So let's sort of start from the most local, which is the instrument-based corrections. So we talked a little bit about how to do flux calibration in these instruments. So in high resolution spectrographs, especially fiber-fed ones, you actually can't do spectrophotometry, basically. It's very, very difficult because you lose the information about the absolute flux at that wavelength because you've spread it out so much now that you're very sensitive in each bin to anything changing. So clouds come in, your blue flux, your blue orders will drop by like 50%. So this is some early data from the HPF commissioning run. This is actually Tabby's star. And what you're seeing here is basically all of the extracted Echelle orders sort of lined up, going from red here to blue here. And you can see the blue light is dropping from one to another really drastically. These are back-to-back observations. And so it's what you need to do, of course, you can't do absolute spectrophotometry, but you do need to correct all of the spectra back to sort of the same level. Otherwise, you're weighting the blue, all of the blue lines you're now saying are not that important for RV information content because you weighted them down. This is also kind of a tricky correction to make, but something that you have to think about. The other thing that varies underneath you is the blaze of the Echelle. So Sam talked about temperature in particular changing the resolution, but there's a bunch of other changes to the Echelle. For example, how you illuminate it. So the position on the Echelle that you illuminate and the angle that you illuminate it at changes the response of that Echelle. So how efficient it is at now giving you light back. And so this is sort of an extreme example showing two different polarization modes on the Echelle. So this is the same wavelength of light going in, but forming two very different intensity curves on your detector. And so if you don't account for it, now your star can vary between these two back and forth, and again, change both the weighting of the lines relative to each other. So what you're saying is more important, but also the shapes of the lines because the continuum is changing underneath it. So this is another correction that you have to think about. The problem is that the blaze actually shows how many photons you've collected. So that is a real signal to noise that you have there. The moment you artificially straighten out that blaze, you're upweighting all of this stuff, which is very noisy, with this stuff, which is very nice. And so this is sort of an open question. People treat it differently depending on what you're trying to do, but definitely something to think about carefully when you're doing these analyses. Sam already showed some of our early data on the drift between the fibers. So this metric is actually really important when people say that our instrument is at 30 centimeters per second now. What they mean is that the fibers are, the difference between the fibers is at 30 centimeters per second. So the difference specifically between your star fiber and your calibration fiber, because that's as good as you can get, right? If your calibration fiber is moving with respect to the star fiber a bunch, then all of your radial velocity measurements are now wrong. And so this is early data from HPF showing that fiber B to C, which is our star and cal fiber, is at about 20 centimeters per second over 12 hours. And this is something that we will keep measuring for every instrument. And this is a great diagnostic of something going wrong in the instrument. The moment the fibers don't move together, that tells you there's something wrong with your temperature stabilization or something up the path. You really have to look at those drift curves, like I said, and look out for cycles, but especially cycles that you expect to see, so daily cycles, seasonal cycles, yearly cycles. Most spectrographs show these. If you have enough data, you can start to correct it out. But this is this is sort of really lifting the hood on bad things that happen during commissioning. So this is HPF data. And over a few days, once we turned on the laser frequency comb, you mostly don't see this stuff with the lamp. You only see it with the extremely good calibrator like the comb. We started to see these daily sort of ramps that were happening. And interestingly, they lined up with the LN2 fill cycle of the instrument. So the instrument is cooled actively, and every time we filled the LN2 tank, it got a little bit heavier and was pulling on the back of the detector mount just a little bit. And then over the day, as the LN2 boiled off, that weight would lighten and that pulling would sort of stop. And this is a very, very subtle effect. We had already engineered against it, but it was still there at a very small level, enough that we could see it at a couple of meters per second every night. And so we're going to fix this in the hardware, but it's really important to look at these results, especially your drift of the fiber, and use it to diagnose instrument systematics that you can cancel out. Because you can imagine if you didn't cancel this out, you would have this extra signature on top of your stellar radial velocity, the activity of the star, and the barycentric correction. So this would be an extra cycle on top of that. Okay, so let's zoom out a little bit more from the instrument. We've corrected all of the instrument effects. Now we have to deal with the fact that we're on Earth. So the first thing we worry about is the barycentric correction. So Sharon already talked about this. I will point out that people have been doing barycentric correction at some level for a while. And even when Jason Eastman and Wright wrote their paper, they showed us how to do it at about less than a centimeter per second. But soon after actually they wrote their paper, they realized that even that was not good enough, not because of precision, but because of wavelength. So first of all, you need to calculate the barycentric motion at the flux weighted midpoint of the observation. So not just the middle of when you open the shutter on your CCD and then close the shutter, but you have to think about how the photons came in and what was the actual mid time of the middle photon. But you also have to worry about the fact that not all of the different colors of photons are coming in at the same time. So like I said, say you have cloudy skies, now your blue photons are taking much longer to come in. So the middle blue photon doesn't come in at the same time as the middle red photon. And so you can't just look at your exposure time, you need to look at an exposure meter, and that exposure meter needs to have some wavelength dependence. So for different colors of light, you have to think about what was the point that starlight got to the barycenter in that color, which is hard. But the way we do it is to have an exposure meter that is sort of dispersed, and you can measure these different mid-exposure times. Okay, on to tellurics. So the first and most obvious problem often is telluric emission. So you have these huge warping lines, very bright lines in the atmosphere that are on top of your stellar spectrum. Most of the time we ignore the regions that have those lines. The times when we can't ignore it is when it often falls on top of a stellar activity indicator. So for example, this is the sodium doublet, and we really want to measure the equivalent width changes in this, and basically at the peak of this doublet. And there is a sodium feature from the Earth that is right on top of it. And so for all of these sky problems, the bottom line, the spoiler alert sort of, is that you need a sky fiber. In this case, you take the sky fiber spectrum and you can subtract it almost directly out of your star spectrum. You might have to scale it a little bit for precision, but turns out this correction is actually not horribly hard if you have a sky fiber, which is nice because almost everything is horribly hard. Telluric absorption is the next problem. So we're all familiar with the big absorption bands from the atmosphere. If you leave those uncorrected, you can get several meters per second error in the visible, and obviously in the near infrared, this gets very bad. But what we sort of deal with this, but then we worry about an even deeper level of telluric contamination, which is microtelluric. So these are lines that are about 1% or less. So they're very, very tiny lines. And at that level, the atmosphere actually creates lines everywhere across your spectrum. So there are lines at about 1% or less that are on top of your spectrum and moving relative to it and changing intensities in a not a very predictable way. It's been shown that if you don't correct these out, then you're limited to at about a 20 centimeter per second level, which if you're, again, trying to get to 10 centimeter precisions to try and find an Earth, you find this Earth over and over again, right? So the solution here, again, is to use your sky fiber, but to use it very judiciously. So you use your sky fiber to figure out the strengths of different species in the atmosphere at a given time. And then you take either a model spectrum or a spectrum at that site that you've taken really carefully with a long exposure time, and you scale it and you try and forward model it out of your spectrum. I will point out that nobody has actually done this yet to the level that we need. Lots of people are working on it, including Sharon and Peter are thinking very hard about it. But this is still an unsolved problem that we better learn to do because data are coming in from the new instruments already. Lastly, spectral contamination in general. So anytime you have something that looks like a spectrum, whatever kind of spectrum that is, moving relative to this black spectrum, which is your star here, you're going to have trouble measuring these lines at the precisions we care about. So you can get this from other stars, so binaries, background objects, close by objects, moonlight, zodiacal light, all of this stuff. The things like binaries you don't always have, you could incidentally have them, but what you always actually have is some level of moonlight contamination. So moonlight really is scattered sunlight. And even when the moon isn't bright, there is some level of scattering that happens in the atmosphere, even though you're not looking at the sun right then. So this is especially bad if you're trying to do a sun-like star, because now your spectrum, contaminating spectrum, looks just like the spectrum that you're trying to measure. And so your cross-correlation mask will actually catch on that and make a little peak. And that peak is going to move relative to your stellar peak with the barycentric velocity. So it's moving at plus minus 30 kilometers per second. And if you don't do anything, that's going to dominate what you measure. So here the sky fiber is actually essential. You need that sky fiber for when sky is bright, you can actually extract that spectrum. So you can get a spectrum of the sky and correct it out of your stellar spectrum. Again, very, very carefully, because anytime you change your stellar spectrum, you're messing with the lines. And so you have to be really careful that you're not introducing new systematics as you correct some known systematics. Okay, star-based corrections. This is sort of what we've been avoiding talking about. And Raphael will talk about this even more, but I'm going to talk about all of the things that you need to measure that your instrument gives you before you can consider very sophisticated statistical processes on them. So our first line of defense is to make our spectrometer bandpass as broad as possible. So the more wavelength you cover, the more you pick up on these known activity indicators. So the calcium H and K lines, the sodium lines, H alpha, the near infrared triplets. So we're having to learn about activity indicators in the near infrared now. And so, for example, compared to HARPS, which ends at about 6800, we really made a push with NUID to go very red, both to get M dwarfs, but also to get these activity indicators. So you have a bunch of activity indicators in your image, in your 2D image, and you've extracted them. This is another example of a spectrograph that tries to cover as many activity indicators as possible. This is the Keck Planet Finder. It has two CCDs, a red and a green channel, and highlighted here are some of the activity indicators that we plan to measure. And actually, so This spectrometer doesn't go blue enough to get calcium H and K, but we care about calcium H and K so much that we built a separate spectrometer just to measure that line, because that's how worried we are about stellar activity. So the first thing you do is measure your favorite and every other activity indicator you can think of. The ways these are measured are still sort of the canonical way. This, for example, is the measurement of the calcium H and K lines from Isaacson and Fisher in 2010. These metrics have sort of stayed the same, but of course people are exploring these for the near infrared as well. So you measure these, and it's very hard to get absolute measurement numbers, but remember that in radial velocity, mostly what we care about is relative changes in the star. So then you look at whether those activity indicators that you just measured show any correlation with your RV. So this is a paper I worked on with Paul Robertson for GJ 581, where we were able to show that, this is sort of the plot to focus on here. The blue are the HARPS RVs, and the red is the relative H alpha absorption. And you can see those track really well for this particular planet. So that's not a planet, that's stellar activity. The really difficult thing about this is that there was a lot of data on the star, but for most little chunks of data, you couldn't actually see this match. And so we had to sort of go to this patch of data where it happened to be that the stellar activity was clearly apparent in the indicators that we were looking at, and the sampling was good enough that we could check how it. So you can imagine if you just had this patch and this patch, it would be very difficult to tell if these things were moving together. And so this is really an argument for why you need not only time on the telescope, but time that is utilized to sample the different scales of stellar activity. And Rafael already talked about this yesterday. Stellar activity happens at time scales of minutes to years, which makes it really difficult because obviously we don't have all the minutes to all the years on any telescope. But we're trying to observe some stars really well and try to back this out. But anytime you're observing, this is something to really worry about, whether you're catching a stellar activity cycle in its entirety. Another activity indicator that I look at a lot, because I work on these stabilized spectrographs where I can now trust the line profile, is the shape of that line profile. And the way, a very common way to look at it is to draw this bisector, which is basically the locus of the midpoints joining the two wings of the CCF. And so for most stars, this bisector has a C shape. And as long as whatever the bisector shape is, it sort of depends on your instrument as well a little bit. As long as it's not changing, you're okay. Because anytime there's a real planet and the whole star is moving back and forth, all of the lines are moving the same way. There's no color dependence there. Anytime there's a change in the shape, you have to really worry about what's going on. I will also point out that it would be nice to measure these bisectors for individual lines, but that's really difficult because lines have very low signal to noise. And so what we do is measure the bisector of the cross correlation function, which, like I said before, is sort of an average stellar line. So the reason the bisector varies is either due to stellar activity. So you can imagine if there is a spot going across the face of your star, then the amount of light that you receive from the red shifted and blue shifted portion of this atmosphere sort of gets obscured at different parts and changes the shape of the line. You can also get it from contamination from, say, a background binary star. So this is what we talked about a little bit before with the contamination. Moving back and forth across your spectrum causes a little peak in your CCF that's now moving, and that can also change the bisector. So you have to really look at how the bisector is changing to figure out why it's changing. So I think a nice example of this is this paper I worked on a while ago with Jason Wright, where there was this Marvel's 1B planet that was announced, which was a hot Jupiter. But then there looked like there was another planet at a perfect 3:1 resonance with the hot Jupiter. And this was the first system that the survey found very suspicious for several reasons. And so when I started looking at it, was the first time we had looked at stabilized high precision spectra for it. There had already been high precision spectra, but it had iodine on it, and so you couldn't actually measure the shapes of the lines. But once I was able to actually measure the shapes of the lines, this, for example, is how much Marvel's 1b was going back and forth. For reference, here's Sigdra, a quiet star, and you'll also measure that this whole plot is only this little bit of this plot. So you can get really drastic evidence of contamination in the bisectors. And then you can try and model it out. In this case, we saw it both in the bisector and the full width half maxes of the lines were changing. And so modeling that, we were able to figure out that this was actually a face-on binary star. So you were seeing just a little bit of the radial velocity of a really big binary companion, which was a very nice evidence of what you can do with stable, clean spectra. I'm not going to talk about observing strategy very much, except to say again that stellar activity happens on different time scales. And so when you have an allotment of time, you should think really carefully about how well you're sampling to begin with the rotation period of the star. Taking observations that are separated over years and sample different parts of that rotation period means you're seeing the star in a different state every time. And so sort of the third prong of instrumental precision, understanding RV activity is time on the telescopes, and the use of that time is really important. So the good news is, even though this is really difficult, we can do it. We are doing it. So pipelines work better than any of the instruments that exist currently. So with really carefully taken data, you can get to about 30 centimeters per second on the quiet stars right now. And there is a new state of the art being established right now as we speak. So in the optical, Espresso is showing that they can get to about 30 centimeters per sky, 30 centimeters per second on sky over a few days on a real star, and they're still commissioning, so this is going to get better. In the near infrared, the state of the art right now is HPF, which is at about 1.3 meters per second over several weeks. And so even though this is difficult, it works. You guys should come work for radial velocity instruments, and I'll take questions. Yeah, so most of the stellar activity is magnetically induced. Spots, granules, flares. So yes, and you have to worry about, are you asking about the longer magnetic cycle? Yeah, yes, the answer is yes, we do. Yeah. So the challenge right now is how best to diagnose changes in the magnetic field. So you look at the known activity indicators, but people are actively hunting for other indicators as well. Because an important thing to note is that really many of your lines have indicators of the magnetic field of the star at some level. The question is, how do you tease that out? Yeah, so the way we're doing it is to, oh, sorry. Yeah, the question is, I talked about flux weighted midpoints of the exposures, but also for the different colors of photons. So do we have several different exposure meters with different filters, or how do we do it? So the way we're particularly doing it is to have a dispersed spectrometer. So it basically makes a low resolution spectrum over time. So it's like having, yeah, it's like having several different exposure meters with different filters on it. But in this case, single one, it's just dispersed. Right. So, the question is, so I said we have a separate calcium HNK spectrometer for the Keck Planet Finder. How do we get that light? Is there a different telescope or a single telescope? So, for the Keck Planet Finder in particular, what we're doing is we have a fiber, and we're picking off just a little bit of the edges of that fiber and sending it to a different spectrometer. And that's a really low resolution, simple spectrometer, kind of like the exposure meter actually. And so it doesn't need a lot of light, just a little bit of a percent or two of the main spectrometer.
Okay, so we're going to head to break now, back at 11. So let's thank